Okay, next we will discuss about uh, factors. So in mathematical foundations for industrial engineering, in which we learn linear algebra, we most likely concern on two kind of mathematical objects. We can say it like that. First is about metrics and how a linear system can be represent in matrix forms, and another things so-called factors. Okay, this one. For these slides in particular, we will learn a little bit more about factors, especially Euclidean vector spaces. Okay, this chapter discuss several things, including um, factors in two-dimensional space, three-dimensional space, and even n-dimensional space in which n can be any integer numbers. And we will focus on this part for these slides, and then later on we will move on to discuss the rest of it. Talking about factors itself, first perhaps we could see the uh, the what we called why should be we need another terms called factors. Okay, um, in in order to do physical quantity classifications, either engineers or scientists or physicists classify physical quantities into scalar, or if you want to measure some things like well, it's a quantity that defined by its numerical value alone. Okay, for example, if you want to measure temperature, temperatures can be used um, to measure how hot some object or some condition is, or the amount of heat in those particular objects or a particular environment. So however, for um, some concept, it is also beneficial if we can represent it not only in terms of its numerical value, but also if we can understand, or it can represent the um, the directions of those particular value. Okay, so factors is some concept that can be used to represent both whether it's magnitude of something, or the numerical value or the scalar value of it, and at the same time it can also represent the the directions of where this value is going into. Okay, so uh, for these specific things that we can represent the directions and the magnitude of it, it will be later called factors, or in this case more specifically geometric vectors, in which we can draw it in a representation of an arrow, where the tail of the arrow represent the initial points of those particular vectors, and the end, the terminal point, the tip of the arrow was the terminal point of the arrows. Okay, and these textbooks denotes the factors in a boldface type and lowercase italic both lowercase bold styled letters like this to represent the factors, and to denote the scalars of the value is normally in italic type, such as this should be italics actually, yeah, a K or V. And then when we want to indicate that the vector V has initial point A and terminal point B, it's normally shown like this one. Okay, and the formula representation, the formula will be look like this. The presentation of the vector will look like this. Okay, V is the vectors, A is the initial point, B is the terminal point. That we learn about geometric vectors. One concept that is explained, I think two concepts that explained in this slide is first something that we call equivalency of a vector. Equivalence of vectors means that when we can say vectors would be equal to each other or equivalent. Okay, and since we know that for a vectors that is equivalent to each other, we need to make sure that both components, whether it's the length of the vector as well as the direction of the vectors is equals. Okay, so it can mean only said is equals. Let's say we have vector v and vector w will be equal if and only if the length of both vectors as well as the directions of both vectors is the same. Okay. Okay, so basically if you draw it, okay, this will be, let's say, vector v, it's also equal vector w. Okay, for another vector, let's say this one z. Okay, maybe it has the same directions. No, yeah, maybe it has the same length but different directions. Okay. And then for factors that is equals to 0, or we call it zero factors, it would be considered as a vector where its initial and terminal point coincide and has length of 0. So we call this one as a zero vector. Now that you know about what is vector, what component vector has, and we will observe several concepts which continuation from the previous concept, like how do we do operations in a vectors. Okay, means what? For example, operations such as how do we add one vectors to another. Okay, if we have two vectors, let's say v and w, perhaps in two-dimensional space, that would be easier to represent like this one. If its positions where their initial points coincides, then the two vectors form an adjacent sides, which is parallelogram. And the sums of these two vectors, v plus w, will be represented by the arrow from both initial point, yeah, from this one. Let's say you have this one, v and w. The initial points is coincide in one particular point, and then you want to sum v plus w. So the result of vw is the vector represented by the initial point of this vw is the same with the v and w, but the end point or terminal point will be an opposite vertex of the parallelogram. So like this one, if you translate it here, from this one also translate here, this will be terminal point of the v plus w. So this would be the vectors. Okay. Another rules that can also relate to the vector operation such as vector addition is something called triangle rules. Okay, so for the triangle rules, basically it's reflect the same concept with parallelogram, in which where you have v and w, where it's two vectors position and it, so the initial point of w and v, uh, point of w is okay. So the initial point of w were the terminal point of v. So the sum of v plus w represented the arrow from the initial point of v to the terminal point of w. Okay, like this one. So v is this one, and then if you put w here, from here to another point, so the sum of these two vectors is this one, v plus w. So basically it's the same with parallelogram if you translate it here. So this is will be the parallelogram of it. Okay. So when we construct v plus w and w plus v would be a triangular rules. Okay. So basically if you have v plus w or w plus v, it's basically the same. Another way to see these vectors additions is by consider it that it will be translations of one vectors to another point. So vector addition is like moving a point. By adding two vectors, you shift it at the end of the vector one vectors by the directions and lengths of the others. Ending up the sum of the vectors will be the endpoints of the second vectors. So for example, the terminal points, so you have v and w. V plus w are positioned so the initial points coincide. Okay, and then the terminal v plus w can be viewed in two ways. First is that, okay, if you put that here, v w, so okay, this one. So basically this one is actually translate v from its this one, the endpoint, to the magnitudes of w with the direction of w. So here, and then the v plus w will be this one. Or the other way around, you can v will be this one, w is this one. So it's like translating v to this initial destination point, and then move it as with the magnitude of these vectors to these directions. So the resulting vector is this one. So this is how you apply the triangular rule with a perspective of translation. Okay, vectors subtractions, basically it's the opposite of the previous concept, in which negative of a vector v denoted by this one minus v. Well, it's actually the same a vector with the same length of v, but it has the opposite directions, or the direction being inverted. Okay, so when you calculate difference of v from w, then we denote it as like this. So it's basically w plus negative v. Okay, so first is this one, the concept of v. The minus v will be the opposite, the same, the vector with the same length but the opposite direction. So now with those triangular rules, when you have this one is w with w negative v, so you put v, the original v, into the opposite direction, and then you can apply the parallelogram. This will be w negative v, or you can also use the um, uh, triangular rules to calculate that. Okay, when we have a scalar multiplication in the vectors, well, it basically means that we want to change the size of the vectors. without affecting its directions. Take example, if you have this v, okay, now you multiplied it with the positive scalar, half of v. So the direction of the vector is equally the same, however, the size of it will be half from previously. But when you talk about multiplied it with negative value, so instead of changing the size, you would also change the direction. Okay, one means it's the same size but different direction. Now, what about the value greater than one? Two phi means like the size of it's double from the previous one. Okay. What about negative 3 phi? So the size of it is 3 times before, and the direction is the opposite from the previous vectors. Another concept is vectors which are parallel and collinear. Okay, vectors parallel and collinear is two vectors where we can consider two vectors or um, co collinear first. Let's say collinear vectors is a vector that have common initial point and lie all the points at the same line with the previous other vectors. So suppose you have v and w. If one vector is scalar multiple of the other one, lie it on a common line, so it's reasonable to say that they are collinear. Okay, so you have this one v, and then you have w is equal to k multiplied by phi. So you don't change any directions, right? You just change the size of it. So all of the points is lie in the same line with the previous vectors. However, it's different with parallel. Two vectors were called parallel. Okay, if it maintains the same directions but does not share any, yeah, this one you see, the direction is the same, it's all going there, but it may not have a common initial point nor any points that coincide in the same line. Okay, and for convenience, what about vector 0 where it has only one dot? It considered to be parallel to all vectors for convenience. When you sum three vectors or more, this addition, okay, these addition operations satisfy the associative law for additions. What does it mean? Let's say you have three vectors u, v, and w. So whichever you add first, u, and then you add v plus w first, and then sum it with the u vectors, it resulting into the same u plus v plus w. So there's no ambiguity when you write like this, because it will result no matter which one you do it first. A simple way to construct these vectors is called tip to tail in the successions when we draw the vectors. From, let's say, from point U, you want to go to plus v, U plus v. So you put the tail of the v at the tip of the u, so you will have new vectors, this one, u plus v. Okay, and then you plus with w, so put it the tail of w here on the tip of the v, and then you have v plus w here, so the end result will be here. Either way, whichever you do it first, the end result is still the same, is these vectors. Okay, so that's about sum of three vectors or more. Okay. Now, since vectors is concerned about not only its magnitude or length, but also its directions, it is common to do when you have a two-dimensional space or three-dimensional space, you can use a coordinate system to represent the factors. Okay, so basically, for let's say if you want to have two-dimensional factors, so you will have coordinates that represent vector v, which in which its component will be relative to coordinate system. Let's say if you have v is equal v1, v2, it's the node of vectors, okay, these vectors, okay, where it start from 0, 0, and its result and tip at the v1, v2, then you just need to write vector v equals v1, v2. It's the same with the vector v for a three-dimensional face. It's v1, v2, and v3. Okay. But this one, you can see that the pattern is it's all origin in 0, 0. What about the one that is not origin from 0, 0? We can see it next. Okay. Yeah, it's still the same with the previous one. Um, this still how to represent a vectors in two-dimensional space and three-dimensional space. Now, what about the factors whose initial point it's not at the origin or 0, 0? Okay, it's easier to consider a factor when okay we have the initial point are not in the origin. Let's say this factor p1, p2. This is another way to represent the factors. Well, it's the node where the initial point p1 is x1, y1, and p2 is x2, y2. So vector p1, pi2 can be represented in, so the second component is x2, yeah, here, x2 minus x1 for the first component, and then y2 minus y1 for the second. Okay, so in that the component p1, p2 can be obtained subtracting the initial point from the original terminal point. Okay, you can see that this is it. Now, if you see earlier, we only shown an example of two-dimensional and three-dimensional space because it's easier to be represented or illustrated. But actually, in a real case data set or a real case problems, the number of dimensional space can be quite large. Can be 3, 4, up until many, like 100, 200, or n. Okay. Uh, this in this case means that we are dealing not only three-dimensional space but also n-dimensional space, and it's often denoted as r to the power of n. And this these factors actually is more often seen in the real case applications, such as when you do calculation with experimental data, storage and warehousing, electrical circuit, graphical image, economics. Many of them utilize the calculation with n-dimensional space. Operations looks complex with the number of dimension, basically all the operations that we discussed earlier is also applied for the n-dimensional space vector, such as how do we check equivalency, how do we multiply it with scalar, how do we the effect of negative value of to that factors. It's all the same, including also the associative rules of it. Okay, I think that's about the first part of this discussion, and I will create another videos for the second, third, and fourth part.